All right, so we're going to review for exam 3, my chapter 13, your chapter 15, Brown. And let's see. Go. Which of the following statements, and referencing this equilibrium equation, this reaction equation, which of the following statements about that equilibrium is false? This is not a good question. I'm going to show you why. If the system is heated, the right side is favored. You can't tell, right? Because we don't know if it's exothermic or endothermic. Most likely, it's exothermic, because you got an element making a compound, and most of those are exothermic. But you can't tell from this. There's also the situation where if you increase the temperature, you get more kinetic energy from your reactants, and it gives them, they exceed the activation energy more readily. So that question is one that we really can't say. This is a heterogeneous equilibrium. We can't say that because it's gas and solid. If the pressure on the system is increased by changing the volume, the left side is favored. If the pressure is increased by decreasing the volume is what you have to do. So if you increase the pressure, is it going to favor the left side? You look at the gases. Here's a gas, that one doesn't count. So you've got 2 moles on this side, 1 mole on that side. If you increase the pressure, it's going to favor the lower number of moles. So it will move to the left. Adding more hydrogen gas increases the equilibrium constant. So the only thing that changes the equilibrium constant is what? Temperature. It will change the equilibrium position, but not the constant. Removing HI as it forms forces the equilibrium to the right. That's true. It will move to replace what you removed. It'll move this way. So, except for the problem with that statement, D is the best answer there. Let's see. I have to scroll this one. Get more than one on there. Nope. Stay. See what? Let's move it down like that. Then maybe I can page to the next one. Which of the following is true for a system whose equilibrium constant is relatively small? So remember that equilibrium constant is our example, our generic equilibrium constant. Products on the top, reactants on the bottom. So if it's really small, that means you have very small amount of product. Most of it stays as a reactant. So let's see, with that knowledge, it will take a short time to reach equilibrium. That's kinetics, right? Equilibrium has nothing to say about kinetics. So A is not the answer. It will take a long time to reach equilibrium. That's another kinetic statement. The equilibrium lies to the left, which means reactants. Yes, that is true. And it can't lie to the right. So C has to be answered. Let's see, can I page? Yeah, there we go. For this system, carbon dioxide plus hydrogen yields carbon monoxide plus water. And it is endothermic. Okay. So if K equals 1.6 at this temperature, and it looks like the temperature is constant, at least for now. We haven't given it any conditions yet, changes. If 0.15 mole each of CO2, hydrogen, carbon monoxide, and water, all at the same temperature, are placed in a 1 liter thermally insulated vessel, which is also it. Then as the system came to equilibrium, okay, if we're going to incorporate the endothermic value, where does it go? It's a reactant, right? So we would put 42 kilojoules here. If we're going to try to ascertain the influence of input of energy, so as the system comes to equilibrium, we've got equal moles of each one, and there's 1 to 1 to 1 to 1. Put them in a liter, insulated vessel. Then as the system came to equilibrium, well, we can calculate, all we can calculate from this is the Q value. Unless we can say, oh, the K equals 1.6. Okay. So K would be what? K would be concentration of CO to the first power, H2O to the first power, divided by CO2 times hydrogen. And that's equal to 1.6. So it slightly favors the product side. Okay? It's a little bigger than 1. And since these are all powers of 1, we can make that statement. It's going to move to the right under these conditions. Okay? So if it moves to the right, it's going to consume some of that energy. Temperature should decrease. So the temperature would decrease, it's one of these two, wouldn't remain the same, wouldn't increase. And the mass of CO2 would increase. No, mass of CO2 would decrease because you're moving to the right. Okay, does that make sense? Give me a second to wrap my head around that one. All right, let's see. 4. Let's see. 4 is based upon this equation. 2 A's yield 2 B's plus 1 C. And at a particular temperature, we have 1.6 times 10 to the 4th. So it heavily favors products by a lot. Addition of chemical B to an equilibrium mixture of the above will what? Okay, if we add B, actually, this doesn't matter. If we add B, we know it's at equilibrium, and we add B, it's going to move it to the left, correct? To cause A to increase. That was easier than I thought it would be. Let's see, I better scroll this one up. Probably got it easier. Yeah. Let's get 2 of them. Yeah. Get 5 and 6. Oh, these are all referencing that earlier equation. Hold on a second. So let me write the equation up here. 2A, it's a gas, that might be important, yields 2B, gas, plus C, gas. Okay, and the K equals 1.6 times 10 to the 4th. Okay, now we can scroll, pick up 5 and 6. All right, we're going to change the temperature. At a higher temperature, we flip from positive favoring products to favoring reactants because this value gets very small. It changes by 9 orders of magnitude at a higher temperature. So, placing the equilibrium mixture in an ice bath. So what does that say? If we increase the temperature, we're starting to shift the equilibrium to the left. No. Yes, to the left, because it gets smaller. So this is at T1, and this is at T2, is 1.8 times 10 to the minus 5. So if we increase the temperature, it shifts from favoring products to favoring reactants. So it means it's exothermic. Because if we add heat here, it shifts things that way, right? And that makes the K much smaller. Okay, now that we know it's exothermic, if we place the mixture in an ice bath, then it's going to shift this direction. So it should cause A to decrease and B and C to increase. So cause B to increase. Okay? How about raising the pressure by lowering the volume? Okay. If we increase the pressure, what effect is it going to have? Gases. So you got 2 here, and you got 2 plus 1 here. So you got 3 more on this side. If we increase the pressure, it should shift to the left and cause A to increase. Okay? Either you got it or you're in zombie land. Right? Say again?
The answer to that is to cause B to increase.
But this one causes A to increase when we change the pressure.
Yeah, but we was just not doing 5 on it.
No, we got that one already. We were moving to 6.
I thought, yeah.
You're zombie land. Yeah. Understood. Okay. No, so now we're separated from that previous, and this is a standalone problem. Which of the following statements concerning equilibrium is not true? Let's see, a system that is disturbed from an equilibrium condition responds in a manner to restore equilibrium. Yep, that's basically Le Chatelier's principle. Equilibrium molecular systems is dynamic with 2 opposing processes balancing one another. Yep. You get the forward reaction, reverse reaction, now they're balanced. The value of the equilibrium constant for a given reaction mixture is the same regardless of the direction from which equilibrium is attained. Yes, doesn't matter if it's coming from products to reactants or reactants to product. That value is constant. A system moves spontaneously toward a state of equilibrium. That is true. Now, it doesn't say anything about how long it takes. You know, that's kinetics, right? But it's on its way to equilibrium. Like I said, I may have mentioned this before. Diamonds, they're on their way to equilibrium by decomposing, actually reacting with oxygen. It'll just take them millions of years to get there. The equilibrium constant is independent of temperature. That's the wrong one. Equilibrium constant is intimately dependent upon temperature. All right, let's see, skip just a little too far. So we have this system. Let's see, Hexa Aqua Cobalt 2 Plus and Tetrachloro Cobalt 2 Minus are different colors. So we can tell, we can see visually which way the equilibrium is moving. When cobalt 2 chloride is added to pure water, the cobalt 2 plus ion hydrates. Okay, so this is a step that forms that species right there. After that's done, then the hydrated form reacts with chloride. Okay. So we add cobalt 2 chloride. What it does is, first it hydrates, and then it reacts with some more chloride and establishes an equilibrium between this complex ion, is what we call it. This complex ion, chloride ion, is equilibrium with this complex ion and water. And that's where we're at right now. That's the equilibrium state. Which statement below describes the change that the system will undergo if hydrochloric acid is added? You have to ask yourself, what does hydrochloric acid do in solution? It completely dissociates. Is that still on the board? Just barely. All right, so it makes hydrogen ions and chloride ions, okay? Which are involved? Which ions are common to this equilibrium? Only the chlorides. So we're adding chloride ions, right? So if we add chloride ions, we should reduce the pink, increase the blue. It's going to shift this way. Now, which statement says that? Should become more blue? Yes. Can't become more pink and blue at the same time. So A is right, B is wrong. Equilibrium will shift to the right? Yes. So A and C are both right. That's why E is the answer. Okay. I think this one also references that, so let me scroll it up on the page. Yeah, it's just those two. That equation right here. Okay. Now we have two hydrogens plus a diatomic X, who knows what it is, yields 2 H2X gas. This should be plus. It's exothermic. Okay. If we add X2 to the system, what happens? If we add X2, it's going to shift this way, right? So it's going to make H2X and give off energy. It will cause H2 to decrease. Yep. If you add X2, it's going to consume some of that until we reach equilibrium again. X2, it will cause X2 to decrease. Okay. Actually, X2 will increase at equilibrium. What happens when you add more X2 is that it consumes some of it to reach equilibrium. But it doesn't consume all of it. So from the initial point to the addition, and then when it reaches equilibrium, it stops right in here somewhere. So you still got some extra X2. So X2 would actually increase at equilibrium. H2X to decrease? No, it's going to make more of that. So A is the answer. That can be confusing. This statement right here. At equilibrium, it's actually a higher value than it was before equilibrium was disturbed. Addition of argon to the above equilibrium. Right, gas, gas, gas. What does the addition of we're using an inert gas here, but actually any gas that you add to this system that's not involved in the reaction will have no effect on its equilibrium position. We could add any other gas. We choose inert gases simply because we're guaranteed they're not going to react. But you could add some other gas in there, and if it had no ability to react, if it didn't influence this, go in anywhere in here, it wasn't coupled in any way, then it would have no effect on the outcome. Okay. Let's see. Here we go. Which of the following statements is true? When two opposing processes are proceeding at identical rates, the system is at equilibrium. Well, yeah, that's true. And since this one says none of the above are true, we can stop there. We could go ahead and look at the rest of them, which would probably be a good idea. Catalysts are an effective means of changing the position of the equilibrium. Do catalysts have anything to do with equilibrium position or constants? No. Catalysts are involved in kinetics. How fast does the reaction get there? Concentration of the products equals that of the reactants and is constant at equilibrium. Not necessarily. They can be any ratio of reactant concentration to product concentration. Depends on the reaction. And that's what the K value tells you. Or whether they're equal, or whether you got more products or more reactants left over at equilibrium. So that was false. That was false. An endothermic reaction shifts toward reactants when heat is added. That goes the other way. Because endothermic puts heat in as a reactant. Add more of it, you get more product. Okay. Let's move to 12. Yeah, I can't do that. You still see it? Just barely. You squeeze it just here. That's not going to behave. I'll just scroll the next one too. Consider this reaction. Missing its plus sign. A plus B yields C plus D, and they're all gases. If we add A, the value of K, upon adding gas A, the value of K, well, this is kind of ludicrous. The value of K is constant for temperature. So which one is that? Does not change as long as temperature is constant. There you go. That's a trick question. Here we go. Okay. Combustion of methane. Let's see, is this balanced? That's methane, yep. Oxygen, carbon dioxide, water, that's true. Let's see, one carbon, four hydrogens, four oxygens. 2 plus 2 is 4. Okay, we're balanced. So it's a source of heat, that means it's exothermic. For the system at equilibrium, which of the following explains what happens if the temperature is raised? We raise the temperature, we should drive the reaction backwards. The equilibrium position should be shifted to the left. So, based upon this expression, left, that's good. And the value of K, okay, we are changing the temperature, so we are going to change K. So if we're exothermic, we know it's exothermic, and we add energy to this side, it's going to shift toward reactants, which means the K is going to decrease because you have a higher denominator and a lower numerator. So the K would decrease. Shift it to the left, and the K decreases. Here we go. I think that point was made in that video with the mechanical voice, as I recall. Sounded mechanical anyway. 14. All right, consider this reaction. Sulfur dioxide plus oxygen yields sulfur trioxide. 2 sulfurs, 4, 5, 6, 6. Okay, we're balanced. Which of the following explains what happens after the addition of oxygen gas? So these are all gases, and we add oxygen gas, so the amount of sulfur trioxide should increase and sulfur dioxide should decrease. The amount of sulfur trioxide increases, so it could be A or E. They're both saying it increases, and the value of K stays the same, or the value of K stays the same. We didn't change the temperature. So it has to be E. Okay. How about, there we go. 15. Consider this reaction. 2 bromine chloride does exist, yields 1 diatomic bromine and 1 diatomic chlorine. What will be the effect on the equilibrium of changing the volume at constant temperature? Let's see, you've got 1, 1, and 2. If you change the volume, that changes the pressure. Does it have any influence on the reaction? No. 2 moles, 1 plus 1 is 2. No effect at all. So no change in equilibrium. So it's either D or E. And then the second thing, increasing the temperature at constant volume. Increasing the temperature. Endothermic. Here we go. So it's like that. So if we increase the temperature, we're going to drive it to the right. And the equilibrium shifts toward products. So the answer is D. (16) is based upon, our old friend, cobalt. Okay, we set it up the same way. Which one describes the system will undergo if silver nitrate is added? Okay, so silver nitrate, I assume it's an aqueous solution, but it doesn't have to be. You could add solid silver nitrate to that solution. And it produces silver ions plus nitrate ions. Okay, so which one's going to be involved in this reaction? Well, neither one of them are in here. But will neither one of them react with what we've got up there? Yeah. Silver will react with and produce solid silver chloride. That effectively removes chloride from the reaction mixture, okay, which will shift the reaction to the left. Okay, so let's see. Become more blue? Nope. Become more pink? Yes. Water will be produced? Nope. Silver ion will react with, no, it won't react with that chloride because it's part of that complex ion. It has to be free chloride before it will react with silver. I think we've got a sample, something like that in our exercise today. So the answer is B. 17. Okay. Ammonia is prepared industrially by the Haber process here, and that's balanced, I can tell. For the reaction, delta H is minus 92.2, makes it exothermic. And K at 25 is K at 25 degrees, which is what that means, double zero. That's standard temperature for reactions. It's not standard temperature for, for the gas laws, but it's standard temperature for chemical reactions, 25 degrees. So that K is equal to 4 times 10 to the 8th. When the temperature of the reaction is increased to 500 degrees, which of the following is true? We increase the temperature to 500 degrees, we're going to drive the reaction back this way. Right? So K for the reaction will be larger at 500. No, it'll decrease. K will decrease if we increase the temperature. Go that way and make more denominator and less numerator. Okay, so that was not it. At equilibrium, more ammonia is present at 500 than at 25. No, it goes this way. So you're consuming ammonia to get there. Product formation at equilibrium is not favored as the temperature is raised. That's true. Doesn't favor the product. Reaction of N2 and H2 to form ammonia is endothermic. Nope. Exothermic. Okay? That was Fritz Haber's problem. At 25 degrees at room temperature, this reaction is favored to produce ammonia. You just put nitrogen together with hydrogen and you get ammonia. Problem was, it's not an equilibrium problem exclusively. It's a kinetics problem. It may favor the production of ammonia, but it'll take forever to get any usable amount. Right? So in order to increase the kinetics, you increase the temperature, like 850 degrees. But he also knew that the equilibrium constant, when he did that, would go the wrong way. So he got kinetics to go, but his equilibrium was destroyed in the process, the favorable equilibrium. So his answer, catalyst. Right? If you got a catalyst, you'll get to equilibrium faster. And it does produce a little bit of this. So the next step, after he increased the temperature and got the reaction to go fast enough, and the catalyst to, well, the increase in temperature overcame activation energy. Catalyst overcame speed of reaction. And then how did he get a usable amount of this out of that whole process? He cooled it down. He would take off, he would have another, what do you call it, a stream from the reaction vessel, and he passed it through a very cold environment somehow. And the boiling point of ammonia is much higher than hydrogen or nitrogen. So these would stay gas, and this would drop out. He would condense it out, and then he would take the gases, run them back through the reaction mixture into the reactor, and get some more. And keep doing that. After about 5 passes, he got his efficiency up to plus 15%, and they could go with that. And you just keep running it 24/7. That's known as the economy of volume. The bigger you make it, the cheaper it is per unit. So we just kept running and running and running and made lots of ammonia. And then all you have to do is oxidize it, and you can make nitrates for explosives. That's exactly what Germany needed at that time. They were going into World War I. Let's see, 18. Here we go. Which of the following are true at equilibrium for this reaction? Uh-oh. I'm missing something here. A. This is the key, and I lost something in translation from the Word document to the PDF. Okay, A is in equilibrium with B. Okay, at equilibrium, A is no longer changing. Yep. Ooh, wait. Yeah, the overall concentration of A is no longer changing. The overall rate of change of concentration of B is 0. Well, that's saying the same thing for B as it was for A. No new molecules of A are converting into B. Now that's false. This equilibrium is on
They're
the
constantly changing. Like
exactly right. I mean, it's furious. You can't imagine how fast these things are happening at a molecular level, right? And the value of B over A is changing in time. Nope. The value of B over A is equal to K. It doesn't change.
A over B, but it doesn't change it over time.
No. Actually, the ratio doesn't change. Yeah. That would be, that doesn't change either. Yeah, the inverse. Okay, B, 19. Already gave the answer. That's staring you right in the face. I can't get it all on the board at once. Consider the reaction which is exothermic as written. So since I'm going to have to scroll, let me write this again over here. PCl5 is in equilibrium with PCl3 and Cl2. There we go. Which of the following changes would result in the production of less? We want to produce less of that one. So which one of these would do that? Let me get the answers up here. There we go. Adding PCl3. Yep. If you add some of this, it's going to shift the equilibrium that way and have to consume some chloride, some chlorine. Removing PCl3. Nope. Remove that one, shifts this way, makes more of that. Reduce the volume of the container. All right, gas, gas, gas. This is 2, that's 1. If we reduce the volume and increase the pressure, it's going to shift this way. It's going to go from 2 to 1. So that was not it. Removing PCl5. Nope, that shifts the wrong direction and consumes. Oh, wait a minute. Less, yes, that one is true. Yeah, that was true. If you remove this, it makes less of that. Increase the temperature. Do we know? Did it tell us?
It says it's up there.
Yes, you're right. Exothermic. So, increase the temperature. We'll drive it back this way. Yes. Produce, oh, I messed up. Increase the temperature would also drive it to the left. Removing PCl5, increase the temperature, reduce the volume.
Yes, because of the lag.
Yes. Removing PCl3, no. And adding PCl3, yes. Increasing the volume of the container. Increase the volume
Makes it dry.
would make more chlorine, wouldn't it? Adding PCl5 makes more chlorine. Reduce the temperature, it would make more chlorine. Adding a suitable catalyst has no effect. Yeah. Okay, so it's Roman numeral 1, 3, 4, and 5. 1, 3, 4, and 5. Here we go. B. Let's see, I better scroll out. We do.
18, 19, 20 is all big.
Okay. Get there. The following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. 2, mercury 2 oxide solid yields 2 mercury liquid and oxygen. I think this is where mercury gets its symbol. It's called hydrogenium. It's oxygen forming. It's based upon this compound. I think that's red. It's a red compound. You heat it up a little bit, it leaves mercury liquid behind plus oxygen gas.
Colors do they have to talk?
Yeah, colors. This is plus, so that's endothermic, right? Allowed to reach equilibrium. The mass of the mercury 2 oxide in the bulb could be increased by. Remove some of this. No, that'll decrease it. Right. Reduce the volume of the bulb. There's a gas. If we reduce the volume, increase the pressure, it's going to get rid of that gas. Right. Even though there's no gas on this side, it will try to reduce that amount to compensate for the increased pressure. So yes, that one will. Adding more mercury will No, it's not even part of the equilibrium because it's a liquid. Liquids and solids don't count.
Only gas.
Gases and solutions will change concentration. Increase the temperature. Let's see. No, it'll drive it this way because it's on that side, endothermic. So that one was computed. Removing some oxygen it would decrease that amount if we remove some oxygen. Okay, so the only one that works is B. Okay, scroll that a little bit. Like that. At 500 K, 1 mole of gaseous ONCl. Not even sure how to name that. Is placed in a 1 liter container. 1 mole in 1 liter means it's 1 molar. So initially, actually, it would be like this. Not at equilibrium yet. 1 molar. At equilibrium, it is 5.3% dissociated, according to this equation. 2ONCl yields 2NO plus CO2. They're all gases. So, at equilibrium, this is 5.3% dissociated, which means if it starts off at 1 molar, what's left after equilibrium? Let's do it this way. Let's use an ice table. How about that? Initially, this is 1 molar. And that's 0 and that's 0. Okay? Now at equilibrium, down here, we have 5.3% dissociated. So 5.3% of this is converted. So we got what? 0.947 molar. Okay. That means we had to lose 0.053 molar there. That means this one is 0.53, 0 plus, and this one is half of that, 0.02. .65 molar. So now we have 0.053 and 0.0265 molar. That's our equilibrium condition. What's the equilibrium constant? Okay, so K is going to be concentration of NO squared, concentration of Cl2, first power, and concentration of O in Cl squared. So we just have to plug in the values, right? NO, 0.053 squared and 0.0265, and then 0.947 squared. Let's see if I did that right. 0.053 squared, 0.0265 times, and then 0.947 squared divided into that. So I get rounded off. Let's see. We had two significant figures. So that should be 8.3 times 10 to the minus 5. Hey. Okay. We had to use the ice table to get that one.
I'll have to use it for the next.
Let's see. Maybe we didn't. Okay. For this reaction, Kp equals 1.16 at 800 degrees. Calcium carbonate yields calcium oxide plus carbon monoxide. The only term in K here is that one. And notice it's Kp. So Kp for this one is going to be the, actually it's not even that. It's partial pressure of CO, and that's equal to 1.16. Okay? This is more than likely in atmospheres. Okay, if a 31.3 gram sample of calcium carbonate is put in a 10-liter container and heated to 800 degrees, what percent of the calcium carbonate will react to reach equilibrium? Okay. Yeah, we might have to do. So, actually, we only have one term on that table, is this one right here. So what's the beginning? 0. What's the change? Well, it's going to increase by X, and we're going to have X down here. So this is equal to X, 1.16 atmospheres is equal to X. That's the partial pressure. And let's see, do we have enough information? Pressure, volume, temperature, moles. Pressure, 1.16 atmosphere. Volume, 10 liters. Temperature, 800 plus 273. And number of moles, question. So we can use the ideal gas equation and solve for moles. So pressure is 1.16 atmospheres. Volume is 10 liters. R is 0.08206. And temperature is 1073. That'll give us the number of moles of carbon monoxide produced. Let's see, 1.16. 10 times that, 0.08206 divide, and 1073 divide. So I get 1.317 times 10 to the minus 2. 1.317 times 10 to the minus 2 moles of CO. Okay, so how many moles of calcium carbonate were consumed? Same amount, right? We just need to convert that to mass, correct? And that tells us how much mass was consumed from this reaction. So we need moles on the bottom, grams on the top, molar mass. So what's the molar mass of calcium carbonate? Let's see. Calcium is 40.08. Carbon is 12.01. And 3 oxygens, 48. So that's 100.09. Times, and I've still got it in my calculator to save times. So that's 1.3186 grams calcium carbonate consumed. Okay. What percent of calcium carbonate was consumed? So this divided by 31.3 grams times 100. Okay. Yeah. I get 4.2%. No, that's not right. I made a mistake somewhere. I better do that over again. 1.16 enter 10 times, yep, 0.08206 divided 1073 divided. There's my mistake. Now times 100.09. And that gives us 13 divided by 31.3. That's 42.1. Okay. That's what we'll do it. And go back and use our gas laws. Okay, 23. This system is 2A yields 2B plus C, very small equilibrium constant. Actually gives us the value. 10 to the minus 6. Initially, 3 moles of A are placed in a 1.5 liters flat. determine the concentration of C at equilibrium. Right? So we have 2A equals 2B plus C. Now, are they all gases? Doesn't say. So we have to assume that all of those terms are incorporated into the K value, right? K equals B squared times C divided by A squared. And that's equal to 2.6 times 10 to the minus 6. Okay. So initially, 3 moles of A are placed in a 1.5 liter flask. Initial change equilibrium. 3 divided by 1.5 is 2. 2 moles. Nothing there, nothing there. So we know which direction it's headed. And this is going to produce, let's see, let's look at the concentration of C. So let's make this one, we're going to add a certain amount of C, which means we're also going to add twice as much B, and it's going to come from this one, 2x. See why I chose that value? I put x as our unknown here because the answer we want is x. 2.0 minus 2x. Okay, so if we plug those values in for b squared, we'd have 2x squared, and then c would be x. And then in the denominator, 2.0 minus 2x squared. And that's equal to 2.6 times 10 to the minus 6. Okay. If we keep it as is and solve for x, what are we looking at? A quadratic. Right. You can see this one expanded. This one times itself would give you the ABC terms of a quadratic. But notice that this is very, very small. So you're not going to have a whole lot of this up there. And in fact, this value is going to be significantly smaller than that value. So what we can do is we can say, this is so small, we can toss it out. Right? Just toss that out. Now we've got 4x cubed, x cubed over 2. Or 2x cubed. Okay? So if we divide this value, let's see. I'm going to reduce it further. 2x cubed. So divide this one by 2. 2.6 exponent there. Divide by 2. And then take the cube root of it. And let me see. Let's see. It would be x to the 1/3 power. The cube root of this would be that to the 1/3 power. So we'll say 1 enter 3 divide and then take it to the power. And I get x equals 1.09 times 10 to the minus 2 molar. 0.01. We'll round it off. Let's see, those are in standard notation, so we've got to convert this to standard notation. So move the decimal place 2 to the left and round it off to 2 places. 0.011 molar. B. There you go.
That was a lot of steps.
That was a lot of steps. Exactly right. It still goes back to the balanced equation, K-value expression, and the ICE table. Okay, 23. Let's see what's cooking at 24. Nitrogen gas reacts with hydrogen gas to form ammonia. No kidding. At 200 degrees C, in a closed container, 1 atmosphere of nitrogen gas is mixed with 2 atmospheres of hydrogen gas. At equilibrium, the total pressure is 2.2 atmospheres. Calculate the partial pressure of hydrogen gas at equilibrium. All right, let's put we may not need this, but let's put it up here anyway. Nitrogen gas plus hydrogen gas is in equilibrium with ammonia. So we're going to need 2 of these and 3 of those. All right. Now we put 1 atmosphere of nitrogen gas and 2 atmospheres of hydrogen gas. At equilibrium, the total pressure is 2.2. So at equilibrium, the pressure of these two together is equal to 2.2 atmospheres. What's the partial pressure of hydrogen at equilibrium? Okay. Notice, I think I'm on the right track here. Notice that when these react, for every 1 nitrogen, you're using 3 hydrogens. Let's see, I want to hop on my horse and ride off in the wrong direction. We know we're going to produce some of this. Let's see, let me get this out of the way. Here. So 2.2 atmospheres is equal to partial pressure of nitrogen plus the partial pressure of hydrogen. Yeah. Oh, plus partial pressure of ammonia. Forgot that, because all of these are gases, right? And it said the total pressure is 2.2 atmospheres at the end. Okay, let's see if we can gain anything from ice on this. Okay, these are initials. That's 0. And we're going to produce some of this, right? So let's say we're adding 2x here, which means we're subtracting 1x here, and we're subtracting 3x there, correct? Because if we add 2 of these, we had to use up 3 of those in 1 of those. So this would be 2x. This would be 2 minus 3x. This would be 1 minus x. Okay, and the total pressure, this one plus this one plus this one, is 2.2 atmospheres. I think we have an equation, don't you? That plus that plus that equals this. So we can solve for x. Correct? Okay, so let's combine all our terms. 1 plus 2 is 3. Right, got that one, got that one. And then a minus x and a minus 3x is minus 4x plus a 2x is a minus 2x equals 2.2 atmospheres. So 2.2, let's move this one over here and that one over there. This would be 0.8 atmospheres equals 2x. Right? Well, that says x is equal to 0.4 atmospheres. But x was this term right here. The question was, what's the partial pressure of hydrogen gas? That says 3x. Wait a minute. X is 0.4. So 3x is 1.2. That's equal 3x. So 2 minus 3x. 2 minus 1.2 is equal to 0.8 atmospheres. There it is. Did you follow me?
No.
Okay. The ice table really helped for this one, clarify the whole problem. And it's a good thing I rewrote it over here because I left that term out at the beginning. I knew we wouldn't be able to use the equilibrium expression to our advantage because it didn't tell us what the K was. All right, 25. We're coming down the wire. Oh.
There's 38.
Okay. Well, let me see. We need to do this. Initially, 2 moles of nitrogen and 4 moles of hydrogen were added to a 1 liter container and got this reaction, which we've seen before. Equilibrium concentration of ammonia is 0.455 at 700. The value of K at 700 for the formation of ammonia. We can do that one with ice table. I think you can do that one. So I think we can skip this one. That was easier than the one before. Okay. Given the equilibrium constants for the following reactions, K1 for this one, K2 for that one, what's the K for the system here? Okay. Let's, all right, we don't need to see this yet. Is that a K? That should be a K. Yeah. Okay. So remember Hess's law when we added things together to get the enthalpy of a reaction? This is where we're headed with this one. We just need to rearrange these so that we can get that. Okay. So this is our target. We need copper 2 oxide on the product side. That's an arrow too. If copper 2 oxide, this needs to be on that side. So we're going to have to rewrite it. Solid, it's a gas. And this yields 2 CuO. And we need 2 of them, right? So that's good, except that now the K becomes, but when you flip your equation, you take the inverse of your K. Okay, so we got this one taken care of. We've got half of our oxygen here, and this one's going to have to cancel out somehow. So We need more copper on this side. We need a half an oxygen here. And we need a half a C copper 1 oxide here. So if we take this one and divide it by 2, like that. That should give us 2 CUs plus 1/2 O2 yields Cu2O solid. And now what's our K? When you multiply by a constant, that constant becomes the power of the K. So it's K1 to the 1/2 power, right? Okay, so let's see, does that give us our CuO is here, 2 of those. Cu2O and Cu2O cancel. 2 coppers. Yep. That's used. And an oxygen. Okay. These 2 together, like that. That one's there. This one's here. Now, what is this one? When you add equations together, what do you do to their equilibrium constants? Starts with an M. You multiply them, right? Okay, so it's K to the 1/2, K1 to the 1/2 times K2 to the -1. Okay, now let's see. Let me scroll up. Get the bottom one in there. Okay. Okay. All right, which one of these fits? Well, there's, I don't see any inverse things here, so we need to move this into the denominator, don't we? K1 to the 1/2 divided by K2. Do we have one that matches that? Yeah, E. There you go. So that was fun. Okay. Let's scroll to the next one. Let's see if we need to do this one. For the reaction given below, 2 moles of A and 3 moles of B are placed in a 6-liter container. At equilibrium, the concentration of A. What's the value K? You can do that one. That's nothing new. 28. Exactly 1 mole of N2O4 is placed in an empty 1-liter container. So that's 1 molar concentration. Allowed to react. It actually decomposes into 2 nitrogen dioxides. If at equilibrium N2O4 is 37% dissociated, what's the value of equilibrium constant Kc? Want to do that one? Okay. So let's put this one over here. I have a feeling we're going to need an ice table. 4 yields 2NO2. Those are both gases, so I'm not going to write gas. Initial change equilibrium. Okay, initial concentration is 1 molar and nothing here. Let's see. It also tells us the conditions at equilibrium. At equilibrium, N2O4 is 37% dissociated. So we actually lose 37% of that, or 0.37 molar. And since this is 2, we're adding 0.74 molar there. So this is what's left over. 0.63 molar. And this one is 0.74 molar. Okay? Well, we can do it now. K is equal to, I'm not going to write these out, I'm just going to say this one squared, 0.74 squared, divided by this one to the first power, right? Because of that one. So let's say 0.74 squared, and then 0.63 divide. So I get 2 significant figures, 0.87. There it is, E. The trick to this one, I think, is understanding what we mean by 37% associated. '29. Hydrogen and iodine yield 2 HI, for which the K is 44.8. That's way to the right at a high temperature. Let me see. If an equimolar mixture of reactants gives the concentration of the product to be 0.5 molar at equilibrium, determine the equilibrium concentration of hydrogen. Let's do that one. I. And the K equals 44.8. Sorry. Try that again. 44.8. That's equal to hydrogen iodide is a gas. This is a solid. That's a gas. Since they don't tell you that, I wonder if this isn't even necessary. Equimolar amount of reactants. So initially we have equal amounts of that and nothing of this. Concentration, let's see, concentration of the product to be 0.5 molar. 0.5 molar. What's the equilibrium concentration of hydrogen? Okay. So in order to get this one, 0.5 molar, we had to lose half of that much of each one. Actually, this is solid, so that doesn't mean anything. Okay. But we lost this much of hydrogen. So this would be X minus 0.25. Well, yeah, this would be equal to 0.5 squared divided by X minus 0.25 to the first power. So that means 44.8 would be divided by 0.5 squared. Okay. And then this is still in the denominator. So if we move this one over there and move that one over there, that means I have to take the inverse of this number and add 0.25 to it. So I get 0.26. X is equal to 0.26. And what's the question? Equilibrium concentration of hydrogen. So X is 0.26 minus 0.25 is 0.01. Is that right? No, that's not right. I did it wrong somehow. I'm gonna have to cheat. Does my explanation make any better sense? Oh, okay. Hold on a second. High temperature. That's the clue. That means, excuse me, that means they're all gases. Yeah, that means they're all gases. So that means this one is X minus 0.25. And now, the equilibrium expression is 0.5 0.5 squared divided by X minus 0.25 times X minus, so it's squared. There we go. And that's equal to 44.8. Okay, the trick to this one is if this one's squared and that one's squared, then this whole term, that divided by that, squared. The total thing squared. So this is the way that one goes. There we go. What that means, that's great. Great news. Because now we can take the square root of both sides. And that means 0.5 over X minus 0.25 is equal to the square root of 44.8. Which is 6.693. Okay. Now we can say, let's bring this one over here and that one over there, 0.5 divided by 6.693 is equal to X minus 0.25. So we just need to divide this one by that one and add that one. So I get 3.2 times 10 to the minus 1 is X. That's X. Hold on a second. What was the question? Concentration of hydrogen. Concentration of hydrogen is X minus 0.25. That value right there. So 0.5 divided by 6.693 is 7.5 times 10 to the minus 2. Yeah. Slid off the edge there. 7.5 times 10 to the minus 2. There we go. My mistake was missing this clue right here.
Because it was in the.
Because I thought this was a solid. Yeah.
And I made a wrong guess.
Yeah, you're right. Right. Okay. 29. Let's see, 30. Consider the following reaction. Given 1 mole of HF 0.362 moles of H2, 0.75 moles. Determine the reaction quotient. All right, you can do that, can't you? Just 1 mole divided by 0.75 is the molar concentration of this one. Calculate that one. Calculate this one. 5 liter flask. Okay, 1 divided by 5.2 for this one. 0.362 divided by 5 is 0.06 something. And then this one divided by 5. Give you the starting concentrations. And then you just use the K expression. Q then would be H2 times F2 over HF. Yep, they're all gases squared. And you just plug in your concentrations, and that give you Q. It should be 0.272. By the way, if it's 0.272, which way is the reaction going to go? If Q is greater than K, that means it's got too much product. And it's going to move to the left. All right, 31. Two nitrogen dioxide yields 2 nitrogen monoxide plus oxygen. If the Kp, you're in pressure units now, is 0.604, find the equilibrium pressure of O2 gas if N2 gas pressure is 0.52 and NO is 0.3 atmospheres at equilibrium. Right, so this is pretty simple. Really, all I really need to do is just set up the problem, and I think you can finish it. Here, all gases. So initial, change, equilibrium. So what's the initial? N2 gas pressure is 0. It tells us what the end result is. Right? Tells us what the Kp is. And then 0.52 for NO. 0.52 atmospheres. And NO, well, that's NO. Excuse me. No, excuse me. No, that's not right. NO2 gas pressure is 0.520 atmospheres. And NO is 0.300 atmospheres. And the Kp is 0.604. Equilibrium pressure of O2. Okay. So this is X. And the K is equal to pressure of NO squared times the pressure of O2 divided by pressure of NO2 squared. So NO is 0.3 squared. That's our unknown, or we could call it X. Just to be consistent. And then NO2 is also squared. 0.52 squared. And this is all equal to 0.604. Yep, we can figure it out. Right, just solve for X. And it should be 1.81 atmospheres. Okay? That was 31. Carbon disulfide and chlorine react according to the following equation. To make disulfur dichloride and carbon tetrachloride. When 2.14 moles of carbon disulfide and 5.85 moles of chlorine are placed in a 2-liter container, it comes to equilibrium, the mixture is found to contain 0.62 moles of carbon tetrachloride. How many moles of chloride are present at equilibrium? Should be able to do this one. Yeah, just set up an ice table. We'll do each time we got a little time. I'll just set it up. Still on camera. Okay. So initially, what do you have? 2.14 moles in 2 liters. So this is 2.14 divided by 2 molar. And this is 5.85 divided by 2 molar. Allowed to come to equilibrium is found to be 0.620 moles of carbon tetrachloride. So down here we have 0.620 divided by 2, still in 2-liter container. Okay, so these are 0 to start with. Here we go. And question, how many moles of chlorine are present at equilibrium? Here. So we had to add plus, let's see, that's 0.310, 0.310 molar there. And this would also be 0.310 molar. This would lose 3 of those. So it'd be minus 3 times that. 3, 9. Okay. And this would be lose an equal amount. Okay. So I take this one, subtract from that one, get this value. This one, subtract from that one, get this value. And oh. 2 into 5.85. .925 molar minus 0.930. Okay, so that's molarity, but this in 2 moles. 3.99? Yeah. 3.99 moles. Did you see how I got that? Right? We determined that we lost this much chlorine, so subtract that from that, gives you the molarity. .9305 is 1.995 molar, but it's in a 2-liter container. So molarity times volume is moles. So 2 times that is this. Okay. I saw some wrinkled brows, so I thought I'd better explain. So we didn't have to even go to the equilibrium expression. We just had to have the balanced equation and run our ice table, and it gave us the answer. All right, 33. Minus 80 degrees Celsius, centigrade Celsius. K for the reaction of N2O4 to 2NO2 is 4.66 times 10 to the minus 8. So at that temperature, is heavily favoring the reactant. Practically nothing of this is produced at that temperature. We introduce 0.047 moles of this into a 1 liter container, 0.047 molar, and let it come to equilibrium. The total pressure in the system at equilibrium will be what? Let's see. We have temperature, we have volume. We can calculate we have to calculate moles, temperature, volume, pressure is the unknown, and moles. We have to calculate moles in 204. To NO2. So we introduce 0.047 moles into a 1 liter container. And there's nothing there of the NO2. And the total system, okay. What's the change? Well, we're going to add 2 here and lose 1 there. And this one's going to be 2x. I got a sneaking suspicion there's a shortcut to this. Let me keep going, just in case my initial thoughts don't work. So K is 4.66 times 10 to the minus 8. And that's equal to 2x squared divided by, minus x, divided by 0.047 minus x. There we go. X is going to be extremely small. So at the very least, we can do away with that term. And then if we say 4.66 exponent minus 8 times 0.047, and then this is going to be 4x squared, right? So we divide this by 4, and then take the square root of it. So x, I calculate is 2.34 times 10 to the minus 5. Okay, so what that tells me is this value is going to contribute practically nothing to the final moles of gas. Right? It's so small, we're actually dealing with that value right there as our moles. So if we solve the pressure, moles would be 0.047, 0.08206 for R. Temperature is, what's 273 minus 8? 193. Okay. And then volume, 1 liter. So if I take that one times 0.08206 and 0.047 times, pressure is 0.74 atmospheres. B. The trick to this one is to realize that this transition to there contributes practically nothing to the overall pressure. It's all based upon the original. that's what I was thinking at the beginning, but I decided to go ahead and slog it out, just to be sure. Sample of solid ammonium nitrate was placed in an evacuated container, heated so it decomposed explosively. Okay. A sample, a very small sample, I hope. So it decomposes to nitrous oxide, laughing gas, and water vapor. At equilibrium, the total pressure in the container was 2.63 atmospheres at a temperature of 500 C, calculated kP. Evacuated container. That's important. All the gas in that container now is this. All of this decomposes into that. Okay, so the K expression is going to be calculate Kp. Okay, so we need atmospheres. Is going to be N2O, P N2O times P water squared. At equilibrium, the pressure is 2.63. So it's this one plus that one is 2.63 atmospheres. Let's do this. N2O, water. We don't need the ammonium nitrate. So initially, you got nothing. And then pressure in the container is found to be 2.63. So we're going to get plus X and plus 2X. Okay. In terms of pressure. And then add these two together, and they're going to be 2.63 atmospheres. Okay? So X plus 2X is 3X, and this divided by 3 is 0.877 atmospheres is equal to X. So that's the pressure of N2O, and then the pressure of the other one, water, is 2 times that, or 1.75. 1.753 atmospheres. So now we can plug these values in here. 0.877 times 1.753 squared equals, let's see, I already got that one in there, so let me square it. And then 0.877 times 2.70. There it is. C. Okay. Ice table comes to the rescue. It does tend to clarify things when you look at it in those terms. Let's see here. Oops, I'm missing a subscript. There. Ammonium chloride yields ammonia and hydrogen chloride gas. 10-gram sample is heated in a 5-liter container to 900 C. The pressure of ammonia is 1.51 atmospheres. The equilibrium constant for the reaction is what? So the only gases we need to be concerned with are this one and this one. Because ammonium chloride is a solid. And at equilibrium, the ammonia is 1.15 atmospheres. Okay? So if it's one, and remember the the pressure value is proportional to the number of moles. So if this is 1.5, oh, excuse me, dyslexic, 1.51 atmospheres for this one, then it's going to be exactly equal for this one, right? Because they're 1 to 1. If you can claim that pressure for this one, it has to be the same for that one. So Kp is going to be those two squared. 1.51 is 1.51 squared. 2.28. B. That make sense? Okie doke. 36. Yeah, get close now. Have to run out of time. Let's see. At a certain temperature, K for the reaction, NO2 to N2O4 is 7.5 liters per mole. If 2 moles of NO2 are placed in a 2-liter container and permitted to react at this temperature. What's the concentration of N2O4? I think that was fairly straightforward. Yeah, I think you can get that one. What about this one? We've seen this one. Oh, before it was ONCl, wasn't it? Now it's NOCl. That's different. Yields NO and Cl2. With a K of 10 to the minus 5, 1 mole pure NOCl and 0.964 moles of pure Cl2 are placed in a 1-liter container. What's the equilibrium concentration of Cl2? All right, this one shouldn't give you any trouble. Just in case, we're looking at 3 gases. Like that. And a K value, 1 mole of pure NOCl, initial, in a 1-liter container. So this is 1 molar. And we also start off with 0.964 molar chlorine gas with none of that. Okay? So that tells you which direction it's going. There's nothing here, so it has to go to the right. So if we're looking for concentration of Cl2, then I would make this one X. It's going to make some of that. It's going to make, oh, excuse me, the other way around. It's going to make 2 X's here. And that means it has to subtract 2 X's there. So we have 1 minus 2X here. We have 2X here. We have 0.964 plus X here. Still on camera, barely. There we go. Okay, so if we set it up here, 1.6 times 10 to the minus 5 equals this one squared, this one to the first power, plus X divided by this one squared. Okay. Once we find X, we have to add it to 0.964. Now, since this is a very, very small K, that means X is going to be extremely small also. So we can say that one's out. It's much, much smaller than 1. And this one should be much, much smaller than 0.964 also. So we should be able to say 4x, let's see, 4 times 0.964, 2 squared times this value, 3.856. 856 x squared equals that value. So if we divide this one by 3.856, and then take the square root of it, that's 2.037 times 10 to the minus 3 added to 0.964 is 0.966. Here it is. Did I lose anybody? Okay. That's good to know. One more. 2NOCl, that's the same equation. Calculate the equilibrium concentration of NO. Oh, and I erased all of it. Okay. What did we set up for NO? Shoot. Here. Okay, I set up a different X for this one. It should be 4 times 10 to the minus 3. That one. Okay? All right. We'll let that one ride.